Yesterday we defined EMR as energy traveling in a wave-like form without the need for a medium. In other words, without the need for a material for it to travel through. Now, we also mentioned a few things, a few characteristics of EMR, causes, characteristics, and so on, but it boiled down to 3 key words. If I wanted you to list me the 3 key words, what would one of them be? Acceleration, yeah. The word acceleration is a key word. We need accelerating charged particles. Not just charged particles, not charged particles that are moving. We need accelerating charged particles. And the reason we need accelerating charged particles, or the word acceleration, is because, somebody said it, changing. Because they produce changing electric and magnetic fields. Moving charged particles generate magnetic fields. Moving charged particles generate electric fields, but that's not enough. We need changing electric and changing magnetic fields so that they will produce more changing magnetic and more changing electric fields, and so on. What's the third word? Good, perpendicular. The 3 key words here are perpendicular. If we summarize it, we would say that accelerating charged particles generate changing electric and magnetic fields. Those changing electric and magnetic fields generate more changing magnetic and electric fields, and so on and so on and so on. Those magnetic fields are perpendicular to the electric fields, and they are perpendicular to the motion of the wave. So if one's on the x-axis, one's on the y-axis, they're going to move along the z-axis. If one's on the z, one's on the x, they're going to move along the y-axis. We always have all 3 axes involved, and 2 of the fields will be on 2 of the axes, and then the 3rd axis is the direction of motion of the wave. So these 3 key words should go a long way towards answering pretty much any of those introductory EMR questions. If you remember these, okay, it should go a long way towards answering any of those. Look for these key words: acceleration, changing, and perpendicular. Now, let's go to that table that we went through yesterday and do that again. Okay, that's our review. We'll be essentially doing the same thing as we did yesterday here. 7 types of EMR. You guys remember the first type? If we rank them in terms of frequency that is increasing, the first kind is radio waves. And radio waves we break down into subcategories. We said yesterday we have AM, we have FM, we have television signals, we have radar, right? What else do we got besides radio? What's next to radio? Microwaves. What comes after? Exactly. What comes after microwaves? Infrared. Notice we've changed the color here, which means that the means of production is a little bit different. Infrared. Infra means below. We're below red. So, of course, next to that, next to below red comes red. Well, red and all the other colors of visible light. Red, orange, yellow, green, blue, indigo, and violet. What comes above violet? Ultraviolet. And then we have X-rays, and then we have gamma rays. Now, radio waves and microwaves are both produced in a similar manner. Generally, we say all types of EMR are produced by accelerating charges, but specifically, radio waves and microwaves are produced by oscillating. Oscillating means going back and forth like this. Oscillating electric charge. We'll say oscillating Q. You know what that means, right? Q. Oscillating charge. Okay, good. Infrared, visible light, and ultraviolet are all produced by transitions of electrons. We'll talk a lot more about that in our final unit of the year. Next unit, we'll start that in May. But basically it boils down to this. Electrons can be on a higher level, and they can go down to a lower level, because that's where they want to be, is the lower levels. Okay, it's kind of like going to a hockey game, and you see these empty seats down in row 2, and you're like, I should go fill those in. Electrons want to go fill those lower levels in first, and as they go down to a lower level, they give off energy, and the energy is in the form of the electromagnetic radiation. So when we make transitions, when electrons make transitions from one level to another, from a high level to a low level, they give off EMR. Now, different transitions result in different frequencies of EMR. So it's not like Like it's not like it's random. Like a specific transition gives off a specific frequency, and a different transition gives off a different frequency of EMR. Right, Isaiah? X-rays are produced by, yeah, it is conceivable that X-rays could be produced by transitions of electrons as well, but it would have to be a really, really big transition. If we use that hockey game analogy again, where we say you got a couple seats in the second row that are empty and we want to go fill those in, well, if you're going to produce X-rays, you're making a transition from like the last row of the sport check zone, like way up in the nosebleeds, way down to the first row. Like a massively big transition could produce a really, really energetic photon of light like an X-ray. But usually X-rays are produced by, somebody said it back there, the rapid deceleration of electrons. Electrons get going really, really fast. We make them go really, really fast by accelerating them through a potential difference, right? QV equals 1/2 mv squared. Get them going really fast and then crash them into a target. And as they crash into that target, they stop rapidly, and the kinetic energy, the big amount of kinetic energy that they had gets transformed into a big amount of light energy, which means it ends up being an X-ray photon. Finally, gamma rays are produced by nuclear decay. What's another word for nuclear decay? Radioactivity, radioactive decay. Okay, in the end, any form of nuclear decay results in having matter turn into energy. Matter is converted to energy. And yesterday somebody asked about this. We said, well, can we generate energy from nothing? Like, doesn't it violate the law of conservation of energy? Well, technically, I suppose it does, but we're not creating energy from nothing. We're creating energy from matter. And conversely, we can convert, we can make matter from energy as well. So really, by rights, we should call it not the law of conservation of energy, but rather the law of conservation of matter/energy. All right. Lastly, we have to be able to identify any frequency, any wavelength, or any energy as a specific type of EMR, one of these 7 categories of EMR. 21 different ranges, but the good news is we only have to remember 3 ranges, and we can figure out the rest from those 3. The 3 ranges that we want to remember, that we want to memorize, and there's no other way around this, are microwaves, visible light, and X-rays. Anybody remember the frequency range for microwaves here? 10 to the what? Yeah, 10 to the 9 to 10 to the 12 hertz. Good. Let's go to X-rays now. X-rays are 10 to the 17. You know, sometimes I forget, like 10 to the 17 to 10 to the 19, or is it 10 to the 20? Well, a nice little way of remembering that is that, well, 10 to the 9, 10 to the 12 is the difference of 10 to the 3. 10 to the 17 to 10 to the 20 is a difference of 10 to the 3. So there's a difference of 10 to the 3 in both of those. Not in all types of EMR, but in those 2 types there is. Finally, visible light is a narrower range, so we got to be a little bit more specific, include a base number for this. These are, every type of visible light is 10 to the 14, but specifically it goes from 4 times 10 to the 14 hertz to 7.5 times 10 to the 14 hertz. So if I give you a frequency of, 6 times 10 to the 14 hertz, it would be visible light. If I gave you a frequency of 10 to the 11 hertz, it would be microwaves. If I gave you a frequency of 10 to the 19, it would be X-rays. 10 to the 21 would be gamma, right? 10 to the 13 would be infrared. 10 to the 8 would be, 10 to the 1 would be radio waves. Like, that's a crazy low frequency radio wave, right? 10 to the 1. But we see that, right? The electrons that are moving back and forth on the wires in our house, the oscillating electric charge in the wires in our house are going back and forth at 60 hertz, 10 to the 1. They generate radio waves. Very low intensity radio waves, very low frequency radio waves as well, but nonetheless, radio waves. So any frequency that you're given, you can either match it against the 3 ranges that we memorize, or you can kind of fill in the blanks of the ones that we haven't memorized. What if I gave you a wavelength? What if I said, here's a wavelength of, let's say, 6.0 times 10 to the negative 7 meters. What type of EMR is that? Well, I didn't give you any wavelength ranges to memorize yesterday, so how are we supposed to figure this one out? Solve for the frequency. And how do we solve for the frequency? Yeah. V is equal to F times lambda, or F is equal to V over lambda. Remember that equation from Physics 20? That's the wave equation. V is equal to F times lambda. The speed of the wave, the speed of any of these 7 types of EMR in a vacuum is? Some of you are going to remember, some of you aren't. If you can't remember, where are you going to find it? On your data sheet, right? What is it, Nick? Yep, good. 3 times 10 to the 8 meters per second, divided by 6 times 10 to the negative 7 meters. Divide those two, it gives me 5.0 times 10 to the 14 hertz. So what type of EMR do we have there? It's visible light, right? Probably in the orangish, yellowish range of visible light. I'm not sure exactly where it would fall, but somewhere in that orangey, yellowy range probably. Now, if you were given an energy, we could do a similar thing for energy with another equation that we haven't learned yet. We'll learn that later on in the unit. But know that you can, given an energy, figure what type of EMR it is based on pretty much the same thing we just did, but with a different equation. That's all. All right, I want to spend just a couple minutes talking now about something new, and that is where the first experimental evidence came for Maxwell's theory of EMR. Remember Maxwell's theory of EMR? Accelerating charged particles generate changing electric and magnetic fields, which in turn generate more changing electric and magnetic fields that are perpendicular to each other. Where's the first experimental support for that come from? Well, it's not a new name. You've heard this name in Physics 20 before. Hertz, Heinrich Hertz. That's a unit for frequency, right? It's not a coincidence that Hertz did some work with electromagnetic radiation, quite a bit of work actually, with electromagnetic radiation, and then got a unit for frequency named after himself. Hertz used what we call a spark gap apparatus. Spark gap apparatus essentially had a wire that had a break in it or a gap in it. We apply a big potential difference across that gap, and electrons that are sitting at one side will eventually, given enough potential difference, jump across the gap or arc across the gap. As they do that, they must accelerate. And Hertz knew this. Hertz knew that they would accelerate. He reasoned that if Maxwell said, since Maxwell said accelerating charges generate EMR, he reasoned that if he could detect EMR when he had these electrons jumping across this gap, then Maxwell's theory must be correct. So his experimental setup looks something like this. I wouldn't lose any sleep over this part of it. This is just what we call a transformer that's used to create a big potential difference. Okay, what's important is what I'm going to circle in green here. The gap, which has, however it got it, a big potential difference. You got an electron sitting right here. There's a big potential difference across that gap. It will cause the electron to jump or arc across the gap. And it does that. As it does that, it accelerates. Now, over here, we've got an antenna set up. An antenna is simply a conductor. Sometimes it's as simple as just a wire. If you have an alarm clock or a clock radio beside your bed, sometimes there's a wire coming from it which serves as the antenna for the radio. In your car, there's often a metal wire, basically, sticking up from the hood or sometimes from the trunk of the car that acts as the antenna for the radio. The antenna is just a wire, a conductor. What happens when electromagnetic radiation strikes a conductor, what happens when EMR strikes this wire or this antenna? Well, if Maxwell is right, and that EMR consists of a changing electric and changing magnetic field, then there should be a current produced, an electric current. Think about that. You got a changing electric and a changing magnetic field. That's going to generate a current in the wire. So Hertz reasoned that if he detects a current in the wire when he flips on the switch and the electron accelerates, then there must have been a changing electric and a changing magnetic field, and it must have come from the accelerating charge. Therefore, Maxwell's theory must be correct. So he flips on the switch, guess what happens? He detects a current in the antenna. There must have been a changing electric field, there must have been a changing magnetic field, and it must have been caused by an accelerating charge as the electron jumped across the gap. So Maxwell's theory must be correct. The type of EMR that was used was radio waves, but understand that this experiment was done in a time when we didn't have like clear definitions of 7 types of EMR. Why would he have used radio waves? Because the easiest way to generate accelerating charges was to have oscillating electric charges, which we now know generates radio waves. In fact, it was him that called them radio waves. It wasn't like he chose to, I think I'm going to use radio waves instead of gamma rays. He did whatever he could to generate EMR, and it just happened to be low frequency, which he called radio waves. Since the beginning of time, we've detected EMR with our eyes. But the first experimental evidence for Maxwell's explanation of EMR came from the detection of EMR this way.